Fab. Okay, in which case, Rebecca, if you can start recording, and we'll just give it a quick pause to have the recording notice start.
Laura, the webinar started recording now.
Wonderful. Thank you, Kate. Welcome everybody to today's webinar, which is focused on an introduction to sewage treatment, hosted by the Wales and West branch, but equally open to anyone and everyone. Just as a quick reminder, again, today's webinar is being recorded. So please, keep your questions in the chat. Microphones are muted and cameras turned off. I'd like to welcome you all. Hopefully, click through the slides if they'll let me. Let's give this a go. There we go. So welcome. Today's presentation has been given by James Bezer, who is our lead scientist in the West at Wessex Water. He joined Wessex, I'm not going to crash his intro, don't worry, but he joined Wessex 5 or 6 years ago as a placement student and has become one of our lead scientists. And I thought he'd be the perfect placed person to give an overview of introduction to waste treatment. We're very conscious that over the last few months/year now that some of the on-site tours that we would have done and indeed have done in the Wales and West branch haven't been possible, and that there was possibly a gap in knowledge or something we could help for new entrants to the industry, such as graduates, in giving that overview from a water company's perspective on what waste treatment entails and the process. So I will hand over to Jamie in a second to give his presentation, and what we'll ask is that if you have questions throughout, please do pop them in the chat, and we will answer as many of them as possible at the end. But for the time being, Jamie, I'll hand over to you and let me know when you'd like me to click through. Thank you very much.
That's brilliant. Thank you, Laura. Good afternoon, everyone. Thank you for coming. As Laura mentioned, I'm just going to give a brief introduction to the water recycling treatment process this afternoon. So I go into a little bit more depth on my background. I will then look at the sort of a broad overview of the treatment process and what wastewater is. We'll go through a couple of different stages of the treatment and some examples of each, and we'll finish off with sort of some of the typical parameters that we look for in the treatment process and why. So if we could go to the next slide, please, Laura. Thank you very much. So as I say, my background is in, I have a BSc in natural sciences where I studied physics, chemistry and maths. And I completed an industrial placement with Wessex Water in 2015 in the process optimization team. That was mainly focused on optimizing chemical dosing associated with wastewater treatment plants. Also looked at energy savings and got involved in various projects looking at optimizing systems and data collection as well, and assisting other scientists with things like odor and fly surveys on sites. In 2017, following completion of my degree, I rejoined Wessex Water as a development scientist, which is effectively an area scientist in training. So in the development scientist role, it was quite broad. It was project-based, going in again, doing the optimization of sites, making sure they're performing, assisting the area scientists, and carrying out some project work focusing on particular years into the area scientist role. And within our area scientist role, each area scientist has a patch with a number of sewage treatment works that they are responsible for monitoring and ensuring that they're running optimally and compliant with their permits, whilst using the least amount of energy and chemical as possible to minimize our carbon footprint. And another big part of the sort of area scientist role is then responding to any operational issues that do arise and addressing these as soon as possible, and being proactive in identifying trends and taking samples and addressing issues before they come up. The last major part of the role really as an area scientist is liaising with the engineering teams to ensure that any new plant that is delivered to site is operable and maintainable and does what it needs to do for the site's performance. following just over a year and a half in the area scientist role, I am now currently on secondment, as Laura mentioned, as the lead scientist, managing a team of 6, which consists of 4 area scientists, a science apprentice, and a regional process scientist who looks after the odour and flies side of things. So that's just a little bit about my background. So if we move on then to wastewater and what wastewater is. So wastewater is a complex variable mixture of waste materials in aqueous suspension solution. So for most of our sewage treatment plants, the effluent comes from domestic sources. So that's household waste. So that's bath water, toilet water, sink dishwater. So that makes up the majority of the flows that we receive at most of our sewage treatment works. But we also have some effluent from industrial activities that come in as well, and that can be a whole range of things, from things like breweries, drinks manufacturers, laundrettes, car washes. So those sometimes have some more interesting components to them, and that's all mixed with varying amounts of ground and surface water depending on the catchment that the sewage work sits in. And as you can imagine, depending on the catchment and the mix of effluent that we get, the sewage can have different physical characteristics, which can be colour, smell, debris, chemical characteristics, and the chemicals we sort of tend to look at more so, or those characteristics, are something called the BOD, which is the biological oxygen demand. So that's usually measured in milligrams per litre, and it's how much oxygen would be used by that 1 litre of sewage if it were to be discharged, say, into the watercourse. So the lower BODs, the better, because it means they're using less oxygen and there's more oxygen available in the watercourse for the wildlife. Say the other ones there that we monitor routinely are suspended solids, ammonia and phosphorus. And then we also look at the strength and the septicity of the sewage coming in. And what we can see there is the graph on the right is a typical diurnal pattern for a domestic sewage treatment works. And what you can see is the flows typically drop off overnight, throughout the night when everyone's in bed, and then they increase throughout the morning and the afternoon as people get up and start using their systems, toilets and showers and baths and things. It then dips slightly in the afternoon, and you have a small peak again in the evening when people get home from work, and that's fairly typical of most domestic sewage treatment works. So if we can go to the next slide, please. Can we go to the next slide, please? Thank you. So looking then at an overview of the sewage treatment process, is typically broken down into 5 stages. So we've got the preliminary treatment, the primary treatment, secondary treatment, and we can have tertiary treatment, and then there's the treatment of the sludge. So I'm not going to be focusing on the sludge treatment today, but we'll go through some examples of each of these other treatment processes. So starting with the preliminary treatment, the preliminary treatment generally consists of the storm separation part and the screening and grit removal. So on the storm separation part, in our treatment plant, we have an FFT valency. It stands for flow to full treatment, and that's the minimum amount of flow that the treatment plant needs to treat before the storm system can be brought into operation. So in wet weather, we have a lot more flow come into the water recycling centres from road drains and gullies and the like. So that comes through. The flows through the treatment plant increase up to this FFT value. And then anything, and if it keeps coming in, it will use the storm system. And the storm system generally consists of screens, which will remove any rag and debris that comes down through the sewer. generally consists of storm settlement, so that will settle out solids and any BOD, any of the oxygen demand that's associated with those solids. And then if the flows continue to come in and the storm storage fills up, that's when it will then spill to the watercourse from the storm system. So by that point, it is really, really dilute. Whilst that's going on, we've still got our flows to full treatment, our permitted flows going through the treatment plant, and that's still treating a good proportion of the sewage, which is coming out then as final effluent. So on the next slide, we have some examples of storm tanks on a couple of our sites. So on the left, so they come in various shapes and sizes. We've got one on the left there showing square storm tanks on the slightly smaller works, and we've got one there on the right showing a round storm tank on a slightly larger works. So these are generally kept empty and left ready for use, and then under storm conditions, that the flows will be introduced to these storm tanks, and they provide that settlement as we've just talked about, and you get the clearer storm effluent weir off out the top and out into the environment. So the next stage in the sort of preliminary treatment process, if that storm system is not used, is it goes through a screening process before going on to the main treatment system. So there's various types of screens that are used, and there's just a couple of examples here. So the one on the left shows a rotating rake screen. So as the name suggests, it's a rake and it rotates. And what it does is it picks the rag up out of the effluent and scrapes it up that red line that you can see there, which is the screen. And so it picks the rag up, scrapes it up, and scrapes it off into the trough. So that's one example of a screen that we see out on some of our sites. On the right-hand side of the page, we have what we call a step screen. So this is a screen that has a quite fine mesh on it, usually sort of 6 millimeters. And what happens is the flow comes in, and when that mesh is clear, the flow can flow straight through and straight onto treatment. As solids and rag come through, that mesh will start to blind, and the level in front of the screen then starts to rise. And it then uses the mesh higher up the screen, which is still clear, and allows the flow to pass through. It will then reach a point where the level reaches a certain predetermined level in front of the screen, and that will trigger a wash. So
Okay, for the reason that I changed the name of the
Apologies, Rebecca. I'm back. I don't know what happened on my internet there. If you can just give me sharing permissions again, and I will continue sharing the screen. Sorry, all.
Now,
Yeah, I know.
Rebecca and Catherine, are you there to just let me know if you're going to be able to give me sharing permissions again?
Yeah, we're here. We can't see you sharing at the moment.
I've just done it. It should be okay now.
Okay.
Lovely. I've got permissions again, so hopefully any second you should be able to share my screen, see my screen again.
yeah, brilliant.
We
Thank
can
you.
see your screen now.
Apologies, Jamie. Sorry about that. Hopefully you won't kick me out again.
No worries. I think I was kicked out as well, so I don't quite know what went on there.
So I think you were just talking through when the level rises on the screen on the right-hand side.
Yeah, so when the level rises to a predetermined level, the screen will then start to rotate, and you can see a rotating brush at the top. And as the mesh rotates round, the brush will then clear any rag and solids that's built up on the screen, and that will go off to a compactor system. So as the screen rotates around, the mesh at the bottom will then be clear, and flow will continue to pass through. So if we go on to the next slide, we've got an image of the compactor system. So on this slide, we can see at the bottom there's an example of a compactor. So again, as that name suggests, it compacts the rag and squeezes all the water out of it. And the water that comes from that rag screenings is returned back through the works for treatment, and the screenings are dropped into a skip and taken off site for composting. So after the screenings process, the next part of the process on many sites is grit removal. And on the grit removal, so if we can just go back one slide, please, Laura, thank you. On the grit removal there on the right-hand side, what these are is typically it's larger channels or chambers where the flow comes in, slows down and allows the grit to settle out. And again, that's then pumped off into skips and taken away from site. So if we can go on to the next slide, please, Laura. Thank you. So the next stage in the process is typically primary treatment. So this is usually consists of primary settlement tanks. So in these tanks, solids settle out. So it works in a similar way to the storm tanks we were talking about. And you can see from the schematic in the middle there, you have the sewage comes in through an inlet pipe and up into the center of the tank. And then what typically happens is that flow then radiates out from the center of the tank to the outlet weirs on the side. And what happens is that the solids and the sludge settle in the tank, it settles to the bottom. And on radial tanks, you have on most of them, you have a rotating half bridge scraper. And that scraper system scrapes the sludge around the tank and into a hopper at the bottom. There's then a sludge draw-off pipe at the bottom of the tank, and that draws the sludge out from the bottom of the tank and pumps it across, typically to sludge tanks of some kind, where it's stored before being removed from site. And then you get the effluent, which is a lot lower, and suspended solids and BOD passes on to the next stage of the treatment process. And there's a couple of images there on the left showing, again, different configurations of a square primary tank and a radial primary tank. So on to the biological treatment process. There's various different processes out there, and there will be different processes used at different sites. They're broadly speaking split into sort of two groups. You can have your fixed film processes where the bacteria that treat the sewage grow on a fixed media, and then you can have ones that are suspended growth treatment processes. So I'm going to talk through an example of each, and we'll start with the fixed film growth process for biological trickling filters. So if we can go to the next slide, please, Laura. Thank you. So here's an example of a biological trickling filter on one of our sites. So you can see it's a big tank, and what it has lots of stone media within it. And you have a center column that comes up in the center, and that's where the flow comes into the filter. So it comes through one side of the filter and up into the center column. And within there's two weirs, and when the flow comes up in the center, it goes over the weirs and it goes across then to the distributor arms on the edge. So you can see that either side of the center column. And within these distributor arms, we have nozzles, sparge holes at certain widths distributed across the arm. And as the sewage forces its way out through those nozzles, that actually drives the filter. So that on many of these biological trickling filters, there's no power actually involved. And it's the force of the sewage when it comes out of the arms that drives the filter round. So as the filter is driven round, the sewage is distributed evenly across the filter surface, and it percolates down through the filter until it reaches the under drain channels. So if we go on to the next slide, we can see a schematic of the filter, so all the way through. So you've got that media, which you can see on here, that continues all the way down through the filter. And as we've just talked about, the sewage comes in through an inlet pipe up into the center, out through the distributor arms, and is then distributed across the filter, allowing the effluent to percolate down through to the under drain channels. You will also notice on this diagram on the left-hand side, there's a bit mentioned air inlets, and that's really important because the bacteria need the oxygen to be able to breathe and provide the required treatment to the sewage. So if we can go on to the next slide, please, Laura. So how does this biological treatment actually work? So what happens is you get a biofilm, a biomass growth on the surface of the stone media. And that biofilm typically needs sort of 3 key things to survive and grow healthily. So it needs food, and that's provided by the sewage. It needs a moist home, and that's sort of given by the media surface, and we have to make sure that the filters are rotating frequently and a certain wetting rate is achieved to make sure that media stays moist and it doesn't dry out. And then it needs the oxygen to breathe, and that's where those air vents come in, and it's really important that we keep the airflow going throughout the filter. On the bottom of this slide here, we can see that you may have noticed on the image that the filter was quite deep. They're typically 2 meters deep, and there's a reason for that, and that reason is that the bacteria that treat the BOD, the biological oxygen demand, they are a bit more resilient, and they're a bit faster growing, so they tend to grow at the top proportion of the filter, and they remove a lot of the load initially as it comes in. And then as you go down through the filter and the load gets less, that gives the nitrifying bacteria, the ammonia treating bugs, time to grow. And then in the bottom portion of the filter, that's where most of your ammonia treatment happens, and your ammonia is then converted away from ammonia and into nitrates and nitrites. And so it gives it that chance for sort of an equilibrium to be reached between the BOD and ammonia, and time for all the bacteria to work on the pollutants in the sewage. And there's some examples there on the right hand side of some of the bugs in there that you might see under the microscope. So as you can see on the top one that's labeled good bugs, they're the typically sort of point sourced organisms, and they're good because they settle well. So where after the biological treatment process, it will pass to a secondary settlement tank. And obviously we want any sludge that's been produced to settle really well. So again, we get the clear top water from the top of the tank, and those good bugs do settle well. The ones highlighted at the bottom, you can see they're quite stringy and spaghetti-like, and they're known as filamentous bacteria. And where we get those in the process, what you can actually get is you get sort of water caught between the strands, and they don't settle as well. So if they start to proliferate, we can get settlement issues with sludge, and you are at risk of a higher carryover of suspended solids in your effluent. So that's an example of a fixed film growth process. So next we will move on to an example of a suspended growth process. So we'll talk about sort of a conventional activated sludge plant. So looking at the diagram in the top left here, we can see that sewage is coming in on the left-hand side, and it's coming into a selector zone. And in this zone, the incoming sewage is mixed with the bacteria held in suspension that are already in the process, and that's provided by this thing called RAS, which I'll come on to a bit more in a moment. So we've effectively got the sewage coming in, and it's mixed with the bacteria already in the process in this selector zone, and then it passes through, in this example, it passes through lanes. And the lanes are designed with baffles so that there's a certain retention time within each lane, again, giving the bacteria sufficient time to treat the sewage as it passes through. And these lanes are typically aerated. So again, that's producing the oxygen demand, the oxygen for the bacteria to be able to treat the pollutants. And there's no media in these lanes. They're just big tanks designed with a certain retention time. So there's a soupy sort of brown mixture in those lanes, and that passes out, and we call that the activated sludge. So that reaches the collection channel at the end, and that mixed liquor activated sludge then passes to a final settlement tank. In the final settlement tank, the solid portion of it settles out, and that's a lot of your bacteria that you've used to treat the sewage, and you get your really clear final effluent treated top water, wears off over the top, and that may either go to tertiary treatment or straight to the environment, depending on the site setup. The bacteria that are collected at the bottom of the tank, in this process, they can actually be reused. So they're returned back to the head of the process, and that's our RAS, that's our return activated sludge. So it's being returned back to the head of the process to be mixed with more incoming sewage and go through the entire process again. Obviously, they are bacteria and they're alive and they reproduce. And so you can get a solids build up within the system. So that's where the SAS comes in on the right-hand side, that red arrow. That's the surplus activated sludge. So every now and again, we have to waste some of that activated sludge and send it off to the sludge tanks to be, again, taken away from site and treated at a sludge treatment centre. So there's different types of configurations of these activated sludge plants and different types of aeration that can be used. So in the lane example at the top, we would typically use fine bubble diffused air, which is a bit like the bubbles you get in a jacuzzi. Another example of how we can get air into these systems might be a surface aerator. And then, so if we look at the diagram in the bottom right there, that's an example of what we call an oxidation ditch. And it's a slightly different setup in that it's a ditch and the flow flows circularly round and round the ditch. But again, it's the same principle, and it's built with a retention time in mind. In this setup, the air is sort of beat in with surface horizontal aerators rather than the fine bubble diffused air. So again, the sewage comes in, it mixes with return activated sludge, which are the existing bugs, spends time in the oxidation ditch, and then wears out into a final settlement tank where we separate out the bacteria and the clear treated effluent. So if we go on to the next stage, next slide, there's some photos of some different processes there. So we can see the photo at the top there shows an aerial view of a more conventional activated sludge lane. So you can see that brown soupy mixture I described, and you can see the fine bubble diffused air there as well. It looks very much like a jacuzzi or a hot tub pattern. So that's your activated sludge treatment. And then you can see in the top left, there's an image of the final tank. So you can actually see it's a lot clearer. All that the brown bugs and bacteria solids have settled out, and you get a really nice clear top water coming off the top. In the bottom and left right-hand images, so if we look at the left-hand side first, we've got an example of surface aerators in a pocket system. So in this system, the flow comes in and it flows through different pockets, and each pocket has its own surface aerator, which really churns up the flow and allows air to enter that system. And then on the bottom right, we've got that oxidation ditch example that I just talked through, and you can see the horizontal rotors there really churning up the flow and again beating that air into the system. So after the secondary treatment process, some sites, depending on the permit, may have a tertiary treatment process, and the need for tertiary treatment will depend very much on the site. So it might be driven by things like the bathing water directive, where you may put UV treatment in to kill any viruses or bacteria and remove that E. coli before it goes out into a bathing water. It might be to meet tighter effluent consent. So perhaps there's a new consent come in that the works that was built 40 to 50 years ago wasn't designed for, so we can add on tertiary equipment to polish the effluent. And it can also be used for sort of nutrient and metals removal with phosphorus, iron, aluminium. So the most common reason for tertiary treatment is really to remove suspended solids, and that removes the BOD associated with it as well. So that actually has an impact on two parameters. And if you're removing solids, if there's any metals in there as well, that will also remove iron and aluminium. So there's lots of different examples there of tertiary treatment systems that you might come across. I'm going to talk through one very briefly, which is the sand filter as an example. So with the sand filters that we use in Wessex, the Wessex Water, there's different systems out there, but we use something called an upflow sand filter. So you can see on the image on the left there that the feed comes in at a high level, and it's then piped down through to the bottom of the sand filter, where the feed flow is then released, and the flow flows up through the sand. And as it passes up through the sand, because the sand is so fine, it traps any solids that are within that effluent and captures them within the sand, and you get a nice clear filtrate come off the top, and that wears out then to your final effluent. So the sand can get quite dirty, so you have a sand backwash pump in there as well. And what that does is that pumps the sand from the bottom of the sand filter up into the central well at the top in the middle of the sand filter. So as the sand's pumped up there, the sand has the right density that it falls down through that labyrinth system that you can see. And as it falls down through the labyrinth and hits the sides of the walls, it knocks the dirt off, and the sand falls back onto the top of the bed. And the dirty water gets carried over to a backwash system, which is returned through the works for treatment. So in this system, the flow is constantly moving up through the bed, and the sand is constantly getting cleaned and moving down. And depending on the setup, it's also possible that you can aerate these sand filter systems, and it does provide ammonia treatment as well, because you can get a biofilm growth on the sand particles. So that's sort of an example of a tertiary treatment system. So I'm not going to go too much, as I said, into sludge treatment, but just a quick mention on sludge. So on most sites, sludge, the solids that are collected in the primary settlement tanks, final settlement tanks, are then sent to either sludge beds or sludge tanks, where it's dewatered, it's tried to be dried out, and then that's tankered away from site. The reason we dewater it and try to dry it out is we want to sort of minimize the number of tankers that we take from site. Obviously, that helps reduce carbon footprint. So we dewater it, and the sludge is removed off site to a proper sludge treatment center, where it will undergo further sludge treatment. On smaller sites, you may not have the sludge beds that you can see on the left there, or the sludge tank that you see in the middle, and it may be more of a septic tank, which is the image on the right hand side there, and that they're emptied periodically, and you can't thicken the sludge there. So that's just a note on sludge. So moving on, so what do we sample on site? So some of the common tests that we do on site to check how the systems are performing is we do a clarity check. So that's checking how clear the final effluent discharge is, and that gives us an indication of the amount of suspended solids that might be in the sample. So that's one of the ways in which we monitor plant performance. We can also carry out on-site ammonia tests as well, and that's often directly comparable with consents and things in our permits. Another test we carry out quite often is this SV test, which stands for settlement volume, and that's the second image along the bottom that you can see on this slide. And what that does is that looks at how well the sludge actually settles, and that helps us to understand how healthy it is and how well it's settling in the final settlement tank. So if it doesn't settle very well, then that's an indication that we've got some of that filamentous bacteria, the bacteria that doesn't settle very well in the system, and we can carry out further investigations as to why that might be. If it does settle well, then obviously that's a really good sign, and it also helps us to gauge whether we've got the right amount of bugs in the system to provide adequate treatment. We also measure the temperature, so bacteria work better at warmer temperatures. So in the winter, they don't always work as efficiently. So we monitor the temperature to make sure that we're at a level where we're happy that we're going to see performance. And then, as sort of touched upon already, we also look at the sludge depths in the tanks to make sure that we get a really nice compact sludge blanket and there's minimal suspended solids carryover. So those are some of the on-site tests we do. Some of the lab tests we do are looking at the biological oxygen demand, the chemical oxygen demand, suspended solids, ammonia, phosphorus, and there can be a few others in there as well, sort of metals analysis, looking at iron and aluminium as well. So those samples are conducted by an accredited laboratory, and we report those samples, and they show compliance with our permits. So on to the next stage as to why we sample. I've sort of just touched on it there. So we sample so that we can monitor the performance of our works and compare the parameters to our consent to make sure we're within our permits. We can use the sample data to identify where baseline levels are starting to rise, and it might indicate early on that something is wrong with the treatment process, and we can actually then step in and put it right before there's any noticeable impact. And it also helps us ensure the process is adequately loaded, because underloading or overloading the process, that can cause its own challenges as well. So those are some of the reasons why we sample. So to summarize on what we've talked about, that the treatment process can typically be considered in 5 separate stages. You've got your preliminary, which is your storm screenings, grit removal. You've got your primary treatment, which is your generally suspended solids removal, and it can be phosphorus removal as well, and that's achieved by mechanical and or chemical methods. You have your secondary treatment, and that's where most of the biological treatment happens. That's the main reduction in pollutants, such as your ammonia and BOD. And that also incorporates some secondary settlement as well. Some sites will have tertiary treatment depending on their permit needs and their needs to meet their permit. And then there's sludge treatment, which we haven't touched upon today, but the sludge produced is typically stored on site, dewatered, and then taken off to undergo its own treatment process at a sludge treatment centre. Thank you very much for listening. So happy to answer any questions.
Fantastic. Thank you so much for that, Jamie. And I'm sure we're all giving you a virtual round of applause for so seamlessly going back in after I think everyone was chucked out and in again. So that was a lovely complexity to add to the Zoom call. So we will try and stitch the 2 halves of the call together. We're not quite sure what we're going to end up with the video, but we'll see what we get. So if you did miss anything in the middle there when we got chucked out, you'll be able to go back and have a look. Yes, if hello, did we just get kicked out again, Rebecca?
There seems to have been about 10 people that went. We don't really know what's going on. We're not doing anything this end.
Okay, well, hopefully I'm back again and you can see questions, and let's just check that Jamie is actually still here.
I was kicked out, but I'm back again.
Wonderful. Okay, fab. At least you're also here, because otherwise we can't answer the questions. I'm not going to try and find the ones that were sent through, because just in case it does pull it down again. So questions that we've had from Giampero Mandola, apologies if I'm saying your name wrong. Do we insert the bacteria, or do we use the ones already in the sewage?
So the bacteria are actually naturally occurring in the sewage, and what we do is we sort of cultivate them and try to grow them more and help them sort of proliferate, and then actually use those properties to treat the sewage. So they're already in the system, in the incoming sewage, and we just help them grow and help them thrive.
Great. And then another question that came through advance that I am going to try and remember off the top of my head was related to dog waste, and can that have an impact on sewage treatment? I don't know if you're able to comment on that.
I think it'd be one I'd have to take away and check with our environmental teams. I don't think it would have. It depends how much dog waste. You know, we do have things like kennels in catchments as well, and that can provide really strong ammonia that comes through the plant, and that can sort of overload the plant. And that might be an example where we then need to get in tertiary treatment to actually make sure that we're still achieving our permits. But in small amounts, you know, any solids are settled out and captured in the process, and any biological oxygen demand or ammonia would typically be dealt with by the treatment process itself.
That's great. Thank you, Jamie. Bill has just put a question through. In Cheshire, there's a considerable volume of field runoff containing fertiliser and animal waste. Is this a problem with your treatment processes? I'm going to jump in and give an answer first, Jamie, and then feel free to contradict me. But Bill, I suspect this is probably more towards the water side of the process, and I'm going to give a quick plug at the end for, we're hoping to repeat this principle of an introduction to, but on the water treatment process at the in January. So keep your eyes peeled for that one. But Jamie, I'll hand over to you to see if there's a waste treatment implication there at all.
So there can be from the some of the field runoff. If it runs into the sewer system, it does mean that there can be higher nitrates and higher loading arriving at some of our treatment works, which can have an impact. So often, if we find an impact, we will look to work with farmers and things to try and reduce that runoff. And minimize that sort of impact. So as I say, if there is anything coming in, we will look to try and minimize that. Depending on the site, it might be able to cope with that loading.
That's great. Thanks, Jamie. And just scrolling through. So Natalie has said, has there been much innovation in wastewater over the years with the standard processes used, or has it stayed fairly traditional?
There have been certain developments. So most of the processes are sort of fairly traditional, but something that the Environment Agency are sort of setting now is consents on phosphorus limits. So that's driven some innovation, in particular in how we actually remove phosphorus from the wastewater treatment process, and we're getting to really low limits on our phosphorus consents. So that starts to involve chemical dosing, and we look at different forms of filtering out those solids and getting to really low levels of solids, because that's what you need to do to remove that phosphorus. So that there's other types of mixed media filters and things that are now starting to come through and be seen, which we haven't previously used. So yeah, there are still good developments in the field.
Great, thank you. And Kian, apologies if I'm saying your name incorrectly. Have you got any knowledge of the Nerida treatment process as a form of secondary treatment?
It's not something I've worked with directly. I have heard of it, and I think we have we do have a plant at one of our sites where we use it to treat high strength liquors, but it's not one that I'm particularly familiar with.
Thank you. Any other questions coming through at all? I'll just give 20 seconds more or so in case anyone's furiously typing away. Oh, one more. How much could a plant like this cost for a city of, I'm guessing, 1 million people? 1 million? How much could a plant like this cost? Jamie, do you have any background in the sort of the capital building side of things, or?
I'm afraid I don't know. No, I'm afraid I can't answer that one. It would be one we'd have to take away and ask our engineering teams and get back to you.
Yeah, and I think actually to head off that, there would be a bit of a how long is a piece of string question as well, in terms of, you know, a type of effluence. We can certainly have a quick chat, but I think it will be subject to many variabilities and vagaries. Any other questions coming through? I'll give it another 10 seconds or so. Right, fantastic. Okay, so I will just repeat my plug that I had a second ago once I can bring up my screens again. So thank you to Jamie again for giving such a fantastic summary of sewage treatment works. People can wax lyrical about this topic for hours, so he did such a fantastic job of summarising the key points into such a short space of time. So thank you, Jamie, for your presentation. That was fantastic. As I said, we will be repeating the principle of this by doing an introduction to water treatment in January, which will be done by some scientist colleagues from Bristol Water. So please keep an eye on the email distribution list or the PIG website if you'd like to sign up to that one. We'll see if there are any more intro twos that we can do across the year. And indeed, there are lots more events coming through from PIG, so please do keep your eyes on there. And actually, I've just seen one question that's come through that I'm going to ask. Do you have any recommended textbooks that can be read, Jamie?
There are some really good textbooks out there. Metcalf and Eddy is a really good one looking at wastewater treatment. There are a couple of others which I can't think of the names of at the moment, but I can certainly find out and get back to you.
I think Metcalf and Eddy is the one that everyone refers to, isn't it? Sort of the Bible of sewage
It
treatment
is,
with
yeah.
many variables. And any special requirements for the pipe materials as well as pipe fittings?
So that we do need to be sort of careful on what we use, because with the sewage coming in, it can be quite septic, and you can get hydrogen sulfide gas produced, and you can actually form sort of sulfuric acid in the sewer when it reacts with the aqueous part of the sewage. So you get quite a lot of corrosion of concrete and things. So pipe materials and things are something that are carefully considered. Quite often we use things like ductile iron, and for ham railing and things we might use steel and things where possible, but it will be considered on sort of a case-by-case basis.
That's great, thank you. Wonderful. Well, if there are any further questions, do pop them over to PIG through email, and we'll see if we can answer them. But otherwise, just may say thank you again to Jamie for giving up your time. Thank you to everyone here for dialing in. Thank you to everybody, PIG, Jamie, everyone for dealing with the slight Zoom kicking in and out. Fingers crossed we can get together a video to put it all together. But have a lovely rest of your day, and hopefully see you on another PIG webinar soon. Thank you very much.
Thank you.